Swayam Prabha. Digital India. Educated India.
Hello and welcome to this course on gas turbines and jet engines. So, today is lecture 5 of this course. Okay. So, this is the final lecture of this first week of the course, and today we are going to learn what are gas turbine cycle with regeneration, okay, or more technically the term is called Brayton cycle with regeneration. So, what is Brayton cycle with regeneration? So, in this class we will cover the concept of Brayton cycle with regeneration, do some analysis and see what are the performance characteristic of regenerative Brayton cycle, try to compare them with the standard Brayton cycle which we have studied in the previous 2 classes. So, now let us take a look at the image which you can see here. So, image shows a TS diagram of a Brayton standard Brayton cycle. Okay. We have our standard 4 processes, heat isentropic compression going from 1 to 2, constant pressure heat addition going from 2 to 3, isentropic expansion from 3 to 4 and constant pressure heat removal from 4 to 1. Okay. Now, what do we notice here for the standard Brayton cycle? We can notice one important aspect, that the exhaust gas temperature is significantly higher than the ambient temperature. Okay. Ambient temperature is T1 and exhaust gas temperature is T4. So, the exhaust gas temperature is significantly higher than ambient temperature. What does it mean? It means that the exhaust gases go out into the atmosphere with a large or considerable quantity of energy being unutilized, and this energy gets dissipated into the atmosphere with the exhaust gases. Okay. And we do not have any direct control over this also, or we cannot. So, if for some reason if you think that we will increase the pressure ratio of the turbine and try to lower the by having a longer expansion process, try to lower the outlet temperature, that is not possible, because the expansion process is bound by the final pressure of the at the exit of the turbine, which cannot go below the atmospheric pressure. So, in this case P 4 should be equal to P 1, there is no option, P 4 has to be equal to P 1, which means that automatically the value of T 4 gets fixed based on T 1 and T 3 and the pressure ratio. Okay. So, this amount of energy then gets wasted. So, the energy which is within the exhaust gas. Okay. So, how can this be utilized? One clever way to do this is to use part of this energy, okay, by using a heat exchanger and passing these exhaust gases through a heat exchanger, use part of this energy, okay, to heat the air which is coming out from the compressor. Let us say that the air comes out from the compressor at state 2. So, by heating from these exhaust gases, its temperature can be raised to, let us say, some value 5. So, this heat comes from the exhaust gases. So, the exhaust gas temperature goes from 4 down to, let us say, some value, let us say here some value 6. Okay. So, the heat exchanger operates with one side working from temperature T2 to T5 and the other side, the combustion product side, going from temperature T4 to T6, okay, like a counter flow heat exchanger. Now, what has happened? Now, we have used part of this energy for the heating and the exhaust gas goes out to the atmosphere at temperature T6, which is much lower. Okay, so, much less energy is wasted, whereas in the combustion part, now the combustion process can start from state 5 instead of state 2. So, the heat addition in the combustion process, heat addition requirement has been significantly lowered, okay, which means that the requirement of fuel is significantly lowered, which means that the efficiency can be increased considerably. Okay. So, this type of process is known as, so this heat addition or heat exchange process is known as regeneration, heat exchange within the cycle itself, and this cycle is called as regenerative Brayton cycle or Brayton cycle with regeneration, and a gas turbine operating on this cycle will be called as regenerative gas turbine or gas turbine with regeneration. Okay. Now, there are certain conditions for which this type of cycles or this regeneration can be done. Let us say that this temperature T4, let us draw another case. Okay. We will draw another cycle, standard Brayton cycle, let us say that, which is a larger compressor pressure ratio. So, like this 1, 2, 3 and 4, larger compressor pressure ratio. So, what do we see here? The outlet condition at the compressor exit, air temperature is already higher compared to the exhaust gas temperature at the exit of the turbine. So, in this case there is no scope of heat transfer from the exhaust gases to the air. If we forcefully use a heat exchanger, the heat transfer will be in the opposite direction, which will lead to more losses and lower efficiency. Okay. So, in this case there is no scope for regeneration. So, regeneration, as you can see, is only possible if the temperature T2 is lower than the temperature T4. So, T2 has to be lower than T4, and larger the difference between T2 and T4, larger is this difference, more is the scope of regeneration, more regeneration can be done and you can get higher efficiency. Okay. So, then what we have discussed till now is schematically it is a regenerator which has a certain effectiveness which is not equal to 100%. Okay. What do I mean by this? Let us consider a case where the heat exchange is perfect, okay, which means that no heat loss occurs and whatever energy is transferred from the state 4, the entire energy is taken up by the air at state 2. Okay. And at the limit that we have infinitely large heat exchanger, we can take the temperature of the air almost to the temperature of the inlet, say exhaust gases which is at the inlet part of this heat exchanger or regenerator. This heat exchanger is called as regenerator. So, this 5 dash point where the temperature T5 dash is equal to T4. This is the maximum theoretically possible temperature which can be obtained in the heat exchanger. Okay. Considering the same mass flow rate for an ideal cycle and same Cp value, this also means that, so by doing energy balance we know that m dot into Cp T5 minus T2 is equal to m dot into Cp, considering the same Cp and m dot value. For real cycles later we will analyze, we cannot use the same Cp values because Cp for combustion products will be different, also the temperature is different, we will take a different value of Cp, and we will also consider different value of mass flow rate due to the addition of mass because of fuel addition. Okay. So, anyway at this point these m dot Cp are same. So, this is T4 minus T6. Okay. This is the general energy balance for a regenerator. General energy balance for regenerator or heat exchanger. Some books you will see that this is mentioned as Brayton cycle with heat exchanger, but better term is to use Brayton cycle with regeneration or regenerative Brayton cycle. Okay. So, in case m dot and Cp are equal, you see that T 5 minus T 2 is equal to T 4 minus T 6. Now, if we can reach the temperature T 5 equal to T 5 dash, in that case if T 5 is equal to T 5 dash, that is it is equal to T 4. In that case, from the energy balance we see that T 6 will be equal to T 6 dash, which is equal to T 2. Okay. So, T 6 will be, so outlet from the heat exchanger for the combustion products will be at the same temperature as the inlet air. Okay. So, this type of heat exchanger is known as a perfect heat exchanger or perfect regenerator, and this is quantified by defining a parameter which is known as regenerator effectiveness. Okay. Regenerator effectiveness. So, for a perfect regenerator, the effectiveness is equal to 100% or 1. Okay. Let us see how to define this regenerator effectiveness. Okay. So, remember, in perfect situation we can reach, theoretically we can reach the temperature T 5 can be equal to T 4 and T 6 can be equal to T 2. Okay. But this is not possible practically, because this will need an infinitely large heat exchanger and infinite amount of time for the heat exchange to occur, because of negligible temperature difference in between the two fluids. Okay. So, for practical cases, the temperature at the exit of the heat exchanger, temperature T 5 will be slightly lower than temperature T 4 and temperature T 6 also will be slightly higher than temperature T 2. Okay. So, now let us see what is regenerator effectiveness. Before that, we will have a quick look at the arrangement of the different components in a regenerative Brayton cycle. Okay. For Brayton cycle, we had seen that there are 4 main components: the compressor, the combustion chamber, the turbine and the heat exchanger for heat removal. So, now because there is a added component regenerator which has 2 intake and 2 outlet, we have to modify the arrangement of the previous components for this cycle. Okay. So, let us try to see how this is done. Parallelly, on the side we will have the cycle also. I will draw it in a slightly smaller size, okay, because we want to draw both the TS as well as the PV diagram. So, we should have sufficient space for that. So, this is for the TS diagram. We have already drawn the TS diagram. Let us say that. These lines are curved, not straight lines. Okay. This 2 to 3 and 4 to 1. So, you need to be careful. Actual lines you can plot using the ideal gas law equations or calculations. Okay. So, now as per our definition, somewhere around this point will be 5 and this point slightly above this point, this will be 6, okay, not the previous one. So, now coming back to this, the arrangement of the components. So, again we have the compressor intake is from the atmosphere at state 1, okay. So, which is the ambient condition. Then after the compression, the air should go to the heat exchanger or regenerator. So, this is the regenerator here, okay. This is like a counter flow heat exchanger, and the air comes and into it at state 2 and goes out at state 5, okay. It goes out at state 5 as already shown here. I am just drawing to show you the directions, and then this air at state 5 then goes to the combustion chamber, okay. This is the combustion chamber. So, this air at state 5 goes to the combustion chamber and comes out at state 3. So, the heat addition in this cycle is from, let us say that it is going from 5 to 3. Okay. Now, for after this, the combustion products go to the turbine, okay, go to the turbine. So, again it goes at state 3 and comes out of the turbine at state 4. Okay. But instead of directly exhausting this to the atmosphere, we have seen that this should now go into the heat exchanger. So, from 4 to 6. Okay. So, this combustion products at state 4 enters. So, at this point we are all means considering only air, although I am saying combustion products. Later on for the actual cycles, this will be combustion products. Okay. This enters at state 4 and after heat loss comes out at state 6. Okay. And then after that it is exhausted into the atmosphere. So, this completes our cycle. This is the component diagram, and the regenerator processes on the TS diagram we can define as going from 2 to 5 and going from 4 to 6. Okay. These two, heat addition and heat means basically the heat exchange process. Now, as we were discussing, we quantify the means how much close to a perfect regenerator we have by defining a parameter called regenerator effectiveness. Okay. So, what is this regenerator effectiveness? So, this is defined in this way. So, again if I for reference we will keep the diagram. I am drawing with this color now. We will draw a quick diagram just for reference, going from 1 to 2, 3, 4. Let us say that this is 5 dash, this is 6 dash, the ideal cases, and real case this is 5 and this is 6. 6 is higher than 6 dash and 5 is lower than 5 dash. So, in that case the effectiveness which is denoted by the symbol epsilon, this is equal to H 5 minus H 2, the actual heat exchange that occurs, divided by the heat exchange in the ideal case H 5 dash minus H 2. Okay. So, this is equal to for constant Cp values, constant equal Cp values, this is equal to T 5 minus T 2 by T 5 dash minus T 2, which means that the regenerator effectiveness is equal to T 5 minus T 2, and T 5 dash is the ideal temperature for the ideal case, which will be equal to T 4 minus T2 as T5 dash is equal to T4. So, this is how the regenerator effectiveness is defined, and if for the limiting case for perfect regeneration, T5 should be equal to T4 and you get a value equal to 1. Okay, T5 becomes equal to T4 when we get a value equal to 1, which means that we reach the maximum possible temperature for the air. Typical values of regenerator effectiveness is of the order of 0.85 to 0.9. Okay. So, around 10% energy is unutilized. Okay. So, this also means that, so for the perfect case, if epsilon equal to 1, okay, subsequently we will be considering the perfect cases for simple analysis. For this case, T5 is equal to T4, because T5 equal to T5 dash, which is equal to T4 from this case. And from energy balance, this also means that, so from energy balance MCP T5 minus T2 is equal to m dot Cp T4 minus T6. Okay. The energy balance from here, okay, for the ideal case, considering m dot Cp is same for the ideal cycle, we get if T5 is equal to T4, okay, then T6 has to be equal to T2. So, T6 will also be equal to T2. Okay. So, these two lines will coincide, the temperature, and these T5 lines also will coincide, and we get the perfect regeneration process. Okay. Now, let us analyze this cycle for this say for this reference value of perfect regeneration. What is the efficiency and work output of this regenerative Brayton cycle? Okay. Again we start with, so in all cases you will see that repeatedly we are drawing the TS diagram, because this is very important. So, we should learn how to draw the TS diagram, and it should be very clear to us how each of the processes occur, what is the sequence, what is the nature of each of the process. So, it is always better to draw the TS diagrams as many times as required for doing analysis. So, 1 to 2 to 3, 4. So, now this will be perfect regenerator. So, this is 5 and this is 0.6. Okay. So, 2 to 5 and 4 to 6 are the regeneration process, and in real life the exhaust gases will go out at stage 6, but we are closing the cycle by using a heat exchanger from going from 6 to 1, okay, just so that we can complete a cyclic process and continue the same cyclic process. Okay. I think we had discussed in the previous class also. Again, I would like to once revise, or let us say that we should know that these processes, these Brayton cycle processes, regenerative Brayton cycle processes, in these cycles all the processes are simultaneously going on continuously, there is no change with time. So, they are steady state, steady flow processes, and all the processes are occurring simultaneously. The working fluid is passing through each of the device and undergoing various changes of state. Okay. This is unlike say reciprocating engines, where the processes occur one step at a time. Okay. Unlike that, here all the processes are going on, simultaneously. When we say a cycle is complete, it is that of the working fluid. So, working fluid is undergoing through multiple processes the same working fluid and coming back to the initial state for the ideal case. Okay. This is important to remember. So, now what is the net work output? How will it change from the simple Brayton cycle? Will it change from the simple Brayton cycle? net work output is T 3 minus T 4 into C p, okay. C p T 3 minus T 4, this is the turbine work output, minus compressor work input C p T 2 minus T 1. Now, we can see that both of these have not changed, T 3 minus T 4 has not changed even with or without regeneration, and T 2 minus T 1 also has not changed, okay. Which means that the net work output remains same for the regenerative Brayton cycle as compared to a standard Brayton cycle or simple Brayton cycle, okay. There is no change, okay, which means that for this case also the performance curves for W net by C p T 1, okay, because T 1 is also same, will remain exactly same as that of simple Brayton cycle or standard Brayton cycle, okay. So, this will be equal to, like in the previous class we had derived, T 1 minus 1 by C. You can easily do the derivation. I suggest that you once again pause and try to do the derivation here, minus C minus 1. So, now there is no change in the work output, okay, no change. Same as Brayton cycle. What about the efficiency? So, efficiency must change, right, because now the heat addition is occurring from 5 to 3 instead of from 2 to 3. So, the heat addition is going from 5 to 3 instead of 2 to 3. So, the efficiency must be changing, right. So, what is the efficiency then? So, work output, net work output remains same, but Q in is different, and the new value of Q in is equal to C p T 3 minus T 5. Okay. So, for regenerator with 100% effectiveness, effectiveness equal to 1, T 5 should be equal to T 4. So, we can simplify this further, simplify the efficiency expression to be equal to W net by C p T 3 minus T 4. So, W net we already know is C p T 3 minus T 4 minus C p T 2 minus T 1, this divided by C p T 3 minus T 4. C p gets cancelled. For this ideal cycle, C p remains constant as already discussed, and this first term we can separate it out. So, this will be equal to 1 minus T 2 minus T 1 by T 3 minus T 4. Okay. So, which we can write as, by taking T 1 and T 3 out from the numerator and denominator respectively, you get T 2 by T 1 minus 1 by 1 minus T 4 by T 3. Okay. So, what is this? T 1 by T 3 is 1 by T. Okay. T 2 by T 1 is equal to, so we have already derived, right. T 2 by T 1 is equal to C, which is r to the power gamma minus 1 by gamma, which is equal to T 3 by T 4. Okay. So, we can write this as C minus 1 by 1 minus 1 by C. Okay. If we take out C as common, okay, we will do it in the next slide. If we take out C as common, then we are left with 1 minus C by T. Okay. Very simple expression for efficiency. But unlike the standard Brayton cycle now, in this case, the efficiency is function of both the pressure ratio as well as the temperature ratio, not only the pressure ratio. Okay. So, this can also be expressed as eta equal to 1 minus r to the power gamma minus 1 by gamma divided by T. Okay. So, now it is a function of both r and T. So, we will finish this part. Okay. We will finish this part with a quick understanding of how the performance characteristics look like. Okay. So, we know for standard Brayton cycle, so we know that the net work output variation will not be there. Okay. There will not be any net work output variation. So, we will draw only the efficiency variations. So, let us say efficiency versus R. For standard Brayton cycle, so at R equal to 1 is the minimum value of theoretical minimum value of R. Efficiency is 0 and then it keeps on increasing like this. Like this. So, for regeneration cycle, so this is for standard Brayton cycle. Regeneration cycle again starting from the minimum value of R, which is 1 theoretically. Okay. For different values of T, so remember what is the efficiency? For this case, this is 1 minus C by T. Okay. Unlike 1 minus 1 by C for Brayton cycle, in this case for regeneration it is 1 minus C by T. We get a complete opposite type of behavior, where the efficiency decreases with increase in pressure ratio. It keeps on decreasing and at some point it goes below the standard Brayton cycle efficiency. Okay. So, let us say that this is for T equal to 5. Similarly, for lower value of T, T equal to 4, it will keep on decreasing, T equal to 3, somewhat like this. So, completely opposite behavior. So, it keeps on decreasing with increasing pressure ratio, while in the standard Brayton cycle there was increase with increase in pressure ratio. Okay. So, this is regeneration and this is standard Brayton cycle. So, I will end this class by suggesting that you think why this is the case, what is the reason that this keeps on decreasing, okay, while for standard Brayton cycle this was efficiency was increasing with increase in pressure ratio. Do not think in terms of the expressions, think in terms of physically what is changing. Okay. Second is what is the limiting values. Okay. Now, the limiting values of at R equal to 1 are not 0, but we get maximum efficiency. What are these maximum efficiencies, limiting value efficiencies, and what is the crossover point? Okay. What is the crossover point where the efficiency decreases below the standard Brayton cycle efficiency. Okay. The crossover point corresponding to so there are different crossover points which corresponds to different values of T. So, what are the crossover points? Means how these are related to other parameters. Okay. So, with this we will conclude today's class, because time has run out. So, today's class we have learned what is Brayton cycle with regeneration and analyzed the regenerative Brayton cycle. We have seen what is meant by regenerator effectiveness, then what is the work output of regenerative Brayton cycle, and what is the efficiency, how it is different for this case as compared to standard Brayton cycle. So, these are the references, the standard set of books, and with this we conclude today's class. Thank you.